In this video, we'll be looking at a variety of different results that deal with circles, arcs, chords, the angles they create and are related to, and circles on the coordinate plane. Let's dive in. First, to define what a circle really is, not just a round shape, a circle is defined as the set of all points in the plane equidistant from some center point. And if you sit and really think about the definition, it should make sense in terms of how to make a circle, which is to take a compass, for example, and stab its needle in a center point and rotate the compass around the radius, which is that equidistant distance. So the circle represents the entire set of all the red points we see on this infinite loop, and they are the same distance from the center point, which I have here in blue. So just an important definition, a straightforward one. It actually leads directly to the idea of a circle on the coordinate plane. So if you think about this as just blank, empty space, and this is how you define a circle, it's any points that meet this definition. On the coordinate plane, where you have numbers, you can use that definition to come up with an equation. That equation of a circle is this, and it looks a little intimidating at first, but if you notice carefully, it has the exact same structure as the Pythagorean theorem, in that it has a quantity squared plus another quantity squared equaling a third quantity squared. And that's not a coincidence. It's a deep part of why circles work. If you think about the distance between the center point, which I have here marked as HK, and any point on the circle itself, which is the black circle here, obviously, then that green diagonal distance is the hypotenuse of a right triangle that has these components for a horizontal change in x and a vertical change in y. And that would be the difference in the x values and the difference in the y values for horizontal and vertical, respectively. So if you think about coming up with expressions for each of these green horizontal and vertical segments, you end up precisely with one leg squared plus the other leg squared equals r squared for the Pythagorean theorem. So just to clarify what this formula means, now that we have some of the rationale behind it, the h and the k represent the center point. So the center point belongs there in the formula or equation. So hk is the center. And similarly, the radius is r. So r squared represents the length of the radius squared, so r by itself is just the radius. Let's take a look at a visual in terms of how this actually functions on the coordinate plane. Here you can see I have typed in, let me scroll this up, the equation of a circle here in this first line with the parameters h, k, and r as mentioned. If I toggle the h key, you'll notice that the circle translates horizontally, hence the variable there. Vertically, and I guess the k in vertical, if you spell it phonetically, k sound at least, the k term is mated to the y value here, which means it should be a vertical change, and indeed it is. And you'll notice whatever the k value is ends up being the center of the circle on the coordinate plane. So right now it's 2, 3.2 is the center, and that's h and k currently for this equation. R, meanwhile, if I adjust r, I should get the radius to change, and you'll see that that is indeed the case. See if I can scroll down here. This is just the radius location. Couple things to mention. One, if you're given an equation, you can come up with where the circle is going to be, because you know that this value and this value will be the center, and the square root of this number that you see, r squared, would be the square root would be the radius. Conversely, if you had the information of center and radius, you can then write the equation of a circle by just knowing this equation and plugging in the numbers that you're given or that you have described for h, k, and r. Going back to the just basic idea of a circle and not so much on the coordinate plane, it's important to define the idea of an angle measurement in relation to circles, which is to say, to express the idea of a radian. A radian is a dramatic, important new topic that kind of is going to break a lot of commonly held notions about angles and how to measure things. All of us measure angles intuitively using degrees, 90 degrees, 360 degrees, and so on. However, it is an arbitrary system. It doesn't have to work that way. A better way, arguably, is to define the radian. A single radian, just as a rule of thumb, a radian is about 57 degrees, give or take. So 2 radians is about twice as much, or about 118 or so, and 114. Half a radian is about 29 degrees or thereabouts. So you can sort of subdivide this 1 radian into bigger or smaller parts as needed, but the amount of turn that this represents is called a radian. And the reason it's a thing is it's built sort of out of this perfect shape, in that this is a radius and this is a radius, so they're the same length, and this length right here is meant to be the same length of these two. And when that's the case, all three of these are the same, and the angle created thusly would be called a radian. Why radian's a thing in more detail, let's take a look at an animation here. A radian is a good way of understanding rotations as opposed to degrees, in part because, as mentioned, the 180, 90, 45 system we're used to is made up. It doesn't have to work with those numbers if you don't want them to. So here's 1 radian. Because the circumference of a circle is the diameter times pi, or 2 radiuses times pi, then the full circumference should be 2 pi radians of rotation. And you'll see that it takes precisely 2 pi of the radius to go around the circle. And thus the angle of rotation there would be 2 pi radians. Or, put another way, a pi radian, so that amount of angle, so 3.14-ish of this angle, so triple it and then add some more, is equivalent, precisely, pi radians is equivalent to exactly 180 degrees. And this typically is the conversion method we use in order to go from radians to degrees, or vice versa. 180 degrees is equal to a little more than 3 of this new system called radians. Quick question, sort of a check for your understanding. How many radians is this angle? Like, how big is it? Well, you'll notice the arc length is 10, the radius is 5, and radian is defined as the angle measurement when, if this is 5 and this is also 5, that this would also be 5. So when you have this circumstance, all three of these are the same, then that is called 1 radian. Well, by the same token, this should be 1 radian as well, right? Because this is 5, and 10 minus 5 leaves 5 for this length. So that should be 1 radian as well, which means the angle here in question would be 2 radians. So theta, the angle, is 2 radians. Or, in general, because 180 degrees is equal to pi, the arc length, or not so much because, but something to know, the arc length, or the length of an arc, is equal to the angle in radians times the radius. So theta, the angle, times the radius. You'll notice that works here too. As we just said, this angle here is 2 radians. So let me clarify here a bit. This angle here is 2 radians. The length of the arc that it captures, this red section here, is precisely 2 times 5, or 10. And that same pattern holds true in general. Sector is the name of the shape sort of created by the radian. It's the entire slice and not just the length. The formula for the area of a sector, and we'll cover this in more detail in the future, but for your reference, the area of a sector is 1/2 times the angle in radians times the radius squared. And one way to remember this formula is, this shape is sort of a triangle circle mixture. 1/2 thing times thing is the triangle area formula, and Greek letter times r squared is the circle area formula. And you kind of have a blending of those two. That's just a little trick to help you remember 1/2 theta radius squared. We've been talking a lot about the section of the circle that defines the radius, which is the arc and the radius. Radian, arc and the radius. It's important to pause for a minute to make sure you understand what an arc is. An arc is a part of the circumference of a circle. So that red section right there is called an arc. And we can consider it through two completely different, or at least quite different lenses. The most common lens is the length, like how long is it from here to here if you actually traveled around the circle like a path. A somewhat more useful approach, or it depends on the context, but a sometimes useful approach is not to consider the absolute length, but the relative size. Which is to say, here I have a circle, and here I have a much larger circle. I'm going to highlight a portion here. It should be fairly obvious that, actually let me do that in a different color. It should be fairly obvious that the blue length here is longer than the red length. So in length terms, this is a longer segment. But in terms of the amount of curvature, or like so the angle this represents out of the full 360, that both the blue and the red arcs are actually the same measure. So we call the amount of curvature of an arc its arc measure. So this can become quite a bit of information, so let me remind you that this is actually something you should already kind of know intuitively in terms of this whole concept. If I take a circle and I cut it into a quarter, well, that quarter is going to be smaller than this bigger circle's quarter if I were to cut it. But the measure of these two arcs would be identical because they both represent a quarter of a circle. It happens to be that this circle is a larger size, and thus its proportion is the same, but its absolute amount is larger. Another important topic about circles deals with chords. Chords, recall, are segments that have endpoints on the circle. So both of these segments you can see here are chords. This other segment I'm about to draw is also a chord, and it's a very commonly used segment. This guy right here would be the diameter. So a diameter is simply a special kind of chord. It's the longest chord. It's the chord that passes through the center of a circle. But in general, a chord is a segment whose endpoints lie on the circle, creating these lines and these little curves and these parts of lines. And there's some interesting patterns that are present among these interchanging bits. If I take two chords and make them cross each other, as we typically do and saw in the last picture, then you have an interesting pattern among these three measures. The measure of arc A and the measure of arc B affect, or sort of, they're in connection with the measure of angle C. So if I were to somehow create a smaller arc here and maybe a smaller angle here, then, or sorry, arc there, then the angle has to change in order to account for that. So A and B and C are all closely related is the main idea here. And that relationship happens to be the following. The measure of angle C, so angle C, is equal to the following results. It's the average of the arc in front of it, arc A, its measure, and the arc behind the angle, arc B. And one way to remember this is that the angle here is physically located in between the two arcs, and the measure of the angle is literally in between the two arcs numerically. The angle here is not as big as A, but it's not quite as small as B. It's in the middle, just like it is physically. It's important to note that these chords do not have to cross in the center. They can, and it's still true. This fact still works, but in general, the chords do not need to cross to the center, and typically they don't. When two chords cross, it's also worth investigating the lengths of their segments and not just the angles of the arcs or the measures of the arcs that they create. So focusing on the actual straight lines here, an interesting pattern emerges among the four pieces created when two chords cross. The result is this. It's that A times B, or the product of the two parts of the segment that are subdivided, here in red, that result, or that product, will be identical to the product of the other segment splits, C times D. The reason this is true, incidentally, if you need to sort of convince yourself of it, is that the two triangles that are sort of created here are similar to each other, and as such, if you do a proportion and cross multiply, you end up with this proportion right here. A is to B as C is to D. This picture looks different than the last few in that these are both chords, but they're crossing in somewhat a different manner. So the last couple of pictures have dealt with this scenario of two chords crossing somewhere inside the circle. However, two chords can also cross on the circle itself, and in that case we call this an inscribed angle. And there's an important result dealing with inscribed angles we're about to look at. One, the inscribed angle here, which is the big sort of angle you can see here in the circle, captures this arc right here. So this amount of this measure I'm going to call x. The central angle, which spans that same arc, so this blue guy right here is called a central angle. Let me make that formal here. Central angle. And this should hopefully make common sense to you, but the angle measure of the central angle is equivalent to the arc on the edge. And again, that can be quite clearly seen with a 90-degree angle. A 90-degree angle captures 90 degrees of 360 of a circle. But in general, these are the same. That's not really that groundbreaking. What's interesting is that the inscribed angle, which is this one over here, has a relationship to x as well, and that relationship is it is 1/2 of the measure of x. So if this right here happens to be 90, then this angle over here would have to be 45. And if this were 80, this would be 40, and so on. If I take two chords, as we have here, and make them cross not in the circle or on the circle, but outside the circle, as you see here, the following result is provable. That result says that the angle measure C, which if you think back to when these two chords crossed in the circle, so let me backtrack a bit. Back when we saw this scenario, the angle was literally physically in between the two, and we added them and divided by 2, so that it wasn't as big as A, but not as small as B. Over here, the angle has gotten even smaller, so adding the two numbers together for A and B shouldn't make a lot of sense because we want to shrink the number. In fact, the measure of angle C is equal to the difference in these two arcs divided by 2. So very similar to the inside the circle intersection. Here, when it's outside, it's simply the difference divided by 2. It's also important to recognize that these two lines are called secant lines. They're lines, or parts of lines at least, that cross through the circle twice. However, the same result is true even if one of the lines is tangent to the circle. So even if arc A was all of this section here as well as what we have, and arc B was all of this, then the green angle would be those two numbers subtracted divided by 2. It also works when both lines are tangent. So what does that look like? Even if you have this scenario, the same result, A minus B divided by 2, will be true. And the last topic sort of deals with inscribed angles as well. A cyclic quadrilateral is also known as an inscribed quad. A four-sided shape drawn inside of a circle. The interesting result here comes from the fact from the inscribed angle theorem that the inscribed angle is half of the arc measure that it captures, which is to say that the red angle here is going to be half of the red arc here, and the blue angle at C will be half of the blue angle, arc that we have here in blue. And because the blue and the red arcs add up to 360, and the blue and the red angles are each half of the red and the blue respectively, what that tells us is this: it's that angle A, or an angle inside a shape like this, combined with the angle directly opposite from it, which in this case is B. When you have this kind of shape, then the opposite angles here will add up to make 180 degrees, for reasons that we've discussed earlier. And likewise, just for clarity's sake, B and D would also add up to make, oops, there's actually a mistake here, A and C, sorry about that. The other result would be, by the way, this is why I was getting ahead of myself, B and D add up to make 180 degrees as well, for the same reasons. Before we wrap up, let's look at a couple of dynamic views of the things we've learned in this long video. Here we already looked at the equation of a circle, so we won't revisit that, but H, K, and R are important. Next, let's look at the inscribed angle theorem, the one we just sort of proved a moment ago, or at least discussed. Here we go. The central angle here is 60. The arc here, which is not marked, is also 60. And I can adjust those to make those smaller or bigger. But the key thing to recognize is the inscribed angle is half of the arc measure. So this is 40 in the middle, and this is 40 on the edge, but this is 20 on the opposite edge. And that's true no matter where this angle's vertex happens to be. It's still half of the arc that it captures. We also saw that when you have chords crossing, that the lengths that it's split into are in proportion. So even though, let me sort of exaggerate this, even though AB, the segment, is obviously smaller than PQ, the parts of AB that are split multiplied together will give you precisely, it looks like about 46 here, will give you precisely the product of the parts that are right here. So these amounts multiplied to give the same as these amounts. Sort of the numbers are trapped within this pattern because of the lines being, or segments being trapped inside the circle. We also saw that the arc measure of an angle, the angle measure of an angle outside is equal to the difference in the two arcs that it captures, and that's true whether it's two secants, whether it's a tangent and a secant, or whether it is a tangent and a tangent. The same fact holds true, which is quite nice. It's the difference in the two arcs that will give you the angle measure. So what else we have here? I think that's it for now. All right, hope this video helps.